Welcome to my talk. My name is Michael Sugimura. I'm going to be going through how we've been combining computer vision and NLP for multitask fashion attribute modeling at Shoprunner. So for starters, what is Shoprunner? And Shoprunner is a Chicago-based e-commerce company which essentially partners with around 140 different online retailers which represent thousands of individual brands. And historically, the core business offering at Shoprunner has been free 2-day shipping and returns. Yes, very much like Amazon Prime. But more recently, we've been starting to develop more data product style offerings to help expand our partner retailer capabilities. And for us at Shoprunner, we have kind of a specific definition for attributes, so I just wanted to go through that here. For us, an attribute is a characteristic of a product that can be applied across multiple taxonomy categories. And a taxonomy category, at least in my brain, is kind of something like a section of a department store. So you have women's shoes, men's shoes, women's dresses, handbags. Those are all examples of taxonomy categories. Then on the other hand, we have attribute categories, which are things like color and pattern, so things that can be applied across these like different taxonomy groups. Then before we go on, the diagram on the right is kind of something I've sprinkled various ones throughout this presentation as a bit of visual flair. But I call these my sample attribute feeds, and essentially these are things that I've generated as parts of presentations internally at Shoprunner to product managers. Basically, the idea is that rather than trying to convey to these folks, like, oh, here's an accuracy score, here's a F-beta score where beta is 0.3, these don't really mean that much to them, and in order to get visceral reactions out of them, I found it useful to sort of generate these feeds, because at the end of the day, what they care about is being able to generate clean feeds in our app and website. So at Shoprunner, it's important for us to be able to standardize these attributes across our product catalog because of the way that we kind of act as an aggregator for like these 140 retailers. And these 140 retailers can send us attributes or sort of descriptions of their products in whatever way, shape, or form that they choose. So one retailer may send you fairly like what sounds like vanilla and simple colors, although color is super complicated. So they may send you things like white, black, blue, red, orange, so very simple. But you might have another retailer which takes a much more artsy, artful approach and say, oh, we're going to send you things like ivory, cream, obsidian, dusk rose, midnight blue, velvet. These are all things that we have in our catalog. And basically, these attribute models provide us a way to sort of, in a very automated way, normalize our entire several million product catalog without having to rely on like manual mappings, which is what folks have done in the past. The other area where we want to apply our attribute models is as feature extractors for other services that we're building. So one such example is kind of visual similarity in search, where we're trying to find similar items in our product catalog. So the overview for this talk, we're going to go through two main areas. So the first of which is this exploring our network architectures. So I'm going to go through kind of the data choices that we made, the overall structure and methods that we used, and then kind of into the individual image, NLP, and then the ensemble models. The next part of the talk is going to focus on kind of some secondary interesting problems that we had to basically solve because of the way that our attribute modeling is working at Shoprunner. So instead of having this like one list of attributes, which would be super practical and super easy to build a data set for and market, what we have is an ever-changing, ever-expanding number of attributes. So we need to be able to very quickly add on a new attribute and deploy it. So we need to figure out some things we had to figure out were how to maintain the weights of our models from previous runs so we don't throw out a lot of useful previous effort, and then figuring out how to physically train that. And for that, our team ended up building out a fairly novel multitask, multi-dataset training pipeline. And then I'll just close out by saying where we're at and where we're going. So start with the network architectures and a fun feed of like paisley psychedelic things. So for our products, we really have like two main sources of data. So that is images and text. And when we look at it and think about attributes, you can think that images, you have multiple images per product, and these images convey certain attributes particularly well. So things like color and pattern. On the other hand, you have text. So this is product descriptions, titles, brand, sizing information. And these encode other sorts of attributes particularly well. So sleeve length, sizing, and cuts are an example of that. And if you think about it, these text attributes are ones that the images actually have a hard time conveying and vice versa. So what we have here is two different sorts of data which provide different perspectives on our products. So they make good candidates for building sort of larger ensemble networks. The other reason why it's good to have these sort of different perspectives or like different types of data and different models is because sometimes we just get products where the data looks weird for one of these two inputs. So this is a product, a pair of jeans, where you can see it's blue, you can see the cut, You can probably like pull out other attributes from that. But if you look at the text has had some weird characters inserted into it, which might be enough to throw off a solely text-based model. On the other hand, we have another pair of genes where, but in this case, the image is fairly nondescript. It looks like a handkerchief, napkin, tablecloth, towel. Take your pick. But in actuality, what it is, it's a very expensive pair of Fendi designer jeans from Italy. But we wouldn't really know that just looking at the images. So now we talk about the data. I'm going to go into sort of our architecture style of choice. And if the title of the talk didn't give it away, it's called multitask learning. And the idea here is that we're basically going to try and get a network to simultaneously optimize to solve a bunch of related tasks simultaneously. And looking online, sort of one of the fun ways that I saw this described was using a pop culture reference to Karate Kid. So in Karate Kid, you have this group of antagonists called the Cobra Kai. And they're basically a bunch of schoolyard bullies who have learned karate as a form of violence. They basically use it to beat people up. So for them, karate is about fighting. But when you look at the Karate Kid, in contrast, when he learns to fight from Mr. Miyagi doesn't teach him how to fight. Mr. Miyagi teaches him a bunch of seemingly unrelated auxiliary tasks. So things like waxing a car, painting a fence, sanding a walkway. And what the Karate Kid doesn't realize is that these tasks are, while he thinks they're pretty dumb, but what they're actually doing is building him up both mentally and physically so that when he learns to fight, he actually learns to fight at a very high level. In fact, he's able to fight better than the Cobra Kai who have only specialized in fighting, like using karate as a way of fighting. So stepping back, some of the things that I mentioned there are talked about in like that metaphorical example with multitask learning is that explicitly it acts as a form of regularization within your neural networks. And what happens here is that a network is basically penalized in training if it tries to over-specialize into a single hypothesis or single idea. Basically, the network has to take a step back, find a more generalized hypothesis to explain all of the different tasks that it's looking at, and then be able to solve them all at a fairly high level. So for us at Shoprunner, we have these varied problems. So things like trying to predict pattern, style, and color. And these varied tasks fall within this similar fashion domain. And technically, we could train up individual networks to solve each of these problems, but each of those networks would likely be learning similar things. So the hypothesis that our team had going into building out these attribute models was that if we can build a single network that trains these multiple tasks simultaneously, we could kind of share the lessons learned on each individual task and build up the model to like a higher level than it would be otherwise. So at Shoprunner, we kind of do a specific type of multitask learning called hard parameter sharing. And the idea here is that you have some core model. It's going to be an LSTM, an RNN, any type of neural network, or any pre-trained model you can think of. And really what we're going to do is take the features from that network and pipe them into individual task layers. And these task layers are the ones that will be doing the classification work. But because of the way that this is set up, these task layers are actually sharing like 99.9% of the weights in this network. And that's sort of what allows this network to share context across these various tasks and build a more generalized understanding of your problem space. So what happens in sort of training is you kind of feed a sample through, and for each task you get their scores and you calculate their losses in a very like standard manner. But you kind of need this unified batch loss in order to, I guess, backpropagate through the network and get it to learn. And when I first started in this area, I thought that sort of getting this batch loss would be actually very complicated. But when you read the research papers and kind of put it into practice, something that's very effective that people try to make sound much more complicated is you literally just add them together. And this is the extent of the math in my presentation. But so once you add these together, you can actually just use that aggregated batch loss as like basically to backpropagate through the network, and this is how the network learns. So one sort of issue that theoretically you can run into here is that you might have one loss that is much higher than the rest. And we haven't personally run into that at Shoprunner yet, but are keeping an eye out for it. And the solution that we see in research is basically just to normalize the losses into more, I guess, normalized range. So before I dive into the network architectures, I just want to talk through kind of our general training protocols for all of these networks. And in general, what we end up doing is when we go to train a new attribute or train a new model, we randomly initialize the new layers. We freeze the weights in the trained sections of the model. And then once we freeze those sections, we can then go ahead and aggressively train the randomly initialized sections. And typically, these new sections won't get up to state of the art, but they'll get up to a good enough point such that when you unfreeze the network and then train everything at a very low learning rate, you get the network to kind of gel together and get to its kind of higher performance. And for the learning rates at this final stage, there's a number of different ways that you can assign it. So one way that has become popular because of like rise of fast AI and a lot of those courses has become to assign learning rates in kind of a gradient from least trained to most trained. Or something that I end up doing a lot in training is just to assign different sections of the network different learning rates depending on how trained it is. So now I'm going to go into sort of our image architecture. And the current version of our image model takes 2 inputs. So it takes a full image of a product and then like the center crop of that full image. We then feed those 2 images one by one through a ResNet 50 architecture and then extract the features out of the final layer. So these are 2 length 2048 vectors that we concatenate together to get that 4096 vector that we then feed through a final dense network. And the idea here is that we can take this sort of large feature vector and condense it down using the dense network, which we can then pipe into these final task layers. And in this architecture, kind of the fun, interesting part is that the fact that we decided to use these cropped images in our final deployed model. And it was motivated because early on, our data science team was kind of brainstorming problems that we would run into with this like attribute modeling pipeline. And something that we thought is that we're actually losing a significant amount of information when we go and take these retail, like high-quality images and resize them down to the 224 by 224 for a ResNet type architecture. So we're losing kind of the detailed context information, which could be useful for certain attributes. So one solution we came up with was if we can find a way to re-inject that context information, it might be able to boost our performance. And something that we settled on was taking a shot using Centercrops. And for me, the center crop thing is kind of fun because it's not motivated by my experience as a data scientist so much as a previous career where I worked as a photographer. So for me, or like basically any photographer, when you start learning how to do photography, regardless of who you learn from or what style you're learning, something that gets indoctrinated into you very early is this idea of the rule of thirds. So you basically draw a tic-tac-toe board, so these vertical and horizontal lines, and you basically try and place objects of interest on these lines or the intersections of these lines. But when you apply this kind of early indoctrination of photography style into like a fashion domain, what you get are very standard-looking pictures, such that if you look across like this, even this small subset where you have outdoor images, indoor images, sort of shirts, dresses, pants, you still get, like if you look at that center box, you're basically getting a good center of mass shot of that product most of the time. So adding the center crops was actually pretty easy to do, and it boosted the performance of our model by several percentage points across our attribute categories. But a downside of this method is that it is pretty simple and pretty dumb, so it doesn't account for things that don't fall into that kind of style. So when we have certain retailers which take more artsy approaches to their images, sometimes we get center crops that aren't actually effective. So in order to mitigate this weakness, things that our team has been working on is really doing a lot of clothing detection type sort of fine-tuning models to in-house data sets, with the idea that if we can use these bounding boxes as a pre-processing step for our attribute models, we're almost guaranteed to get a good center of mass shot of that product. Then the next step we're thinking about is doing segmentation, so fine-tuning these models to basically use the binary mask generated by them to kind of take a product out of an image and place it on a white background, such that we can get a very apples-to-apples comparison to kind of things in our product catalog and things that the model would have seen during training. So now I'm going to go into sort of the NLP part of the model architecture. So for us, the text fields that we're using are things like product name, description, brand, and whatever other sort of information retailers choose to provide. And we're basically feeding this into a BERT architecture. And I'll go into more details about what BERT is, but for all you have to know for right now is that it's a very large architecture which has been very good at an NLP-type task. And we take the features out of BERT and pipe them directly into a series of linear task layers. So this architecture looks pretty straightforward, which it is. But it's kind of motivated by what other folks have been doing in the field. So for instance, there was a group out of Microsoft who published an architecture called Big Bird, so yet another strange Sesame Street name for an architecture. But essentially what they did is they found they could get state-of-the-art results just by training BERT in a multitask fashion. And basically, because of the multitask training, it has to learn to generalize better than a single-task BERT model. Or there's some other groups out of Stanford who are doing similar work around multitask BERT architectures. So BERT as an architecture was released at the end of 2018 by Google, and while most language models are trained in kind of using the left side context of a sentence to predict the right next word, what happens in BERT is it basically takes in the entire sentence And in training, it masks out certain words and uses the left and right side context of that word to kind of predict the masked out one. And Google found this to be a robust training methodology. And like other language models, it's trained on large corpuses of data, so all of Wikipedia, plus whatever other data sets Google had on hand at the time. And really, it and the other, I guess, language models that have come out over the past year, year and a half, are facilitating this kind of very fun ImageNet type moment for the NLP field. And what I mean here is that historically it's been hard to apply state-of-the-art NLP architectures to industry problems because most people just don't have as much data as Google, Facebook, or Microsoft, shockingly. And by publishing these kind of weights and making them open source, it means that practitioners in the field, such as myself, can take them and basically fine-tune them to industry tasks very quickly. And as sort of some implementation notes for the BERT architectures that we're using at Shoprunner currently, it's maintained by a group called Hugging Face out of France, so another interesting name. And their library is called Pytorch Transformers. It's super cool if you haven't had a chance to look at it and are looking for a way to kind of crack an NLP problem. Because they've built out ways to sort of load and save these Pytorch models. They've built out the tokenizers, so you don't have to worry about how to pre-process your data for these different language models. And really, they can be trained up like any sort of standard Pytorch model. So if you have existing pipelines, you can actually integrate them very quickly and get a model up and running in a very short period of time. So now we'll get into our ensemble. So our ensemble is really going to be taking kind of the architectures and kind of smushing them together. So we have our inputs that we look at for the ensemble. So it's a full image, the cropped image, and the various text fields. Then we're basically going to pipe the respective data points through their respective models. And instead of having those output final task layers, we're actually just going to take the final feature vectors from each of those models, concatenate them together, and feed them through another dense network, with the idea that this dense network is really going to be doing the heavy lifting to combine the knowledge of these two models and feed them into these final task layers. And essentially what we found with this architecture is that we've been able to train it on a number of attribute categories and expand the number of categories, and that it has continued to perform well. And so in like the worst case scenarios for certain attributes, we get the highest score from the respective model. But typically we get a several percentage point boost over sort of either model individually. So these models are typically becoming greater than the sum of their parts. So now I'm going to get to the sort of problems that we had around expanding to new attribute categories. And because of the way that we have this ever-growing, ever-expanding list of attributes, we had to think carefully about how to maintain the weights from our previous runs to basically make sure we didn't throw out a bunch of effort. Because in simple terms, if we just try and force an architecture or weights into a slightly different shaped architecture, your, I guess, a deep learning framework will probably throw a bunch of weight errors, at least I hope so. And then if you aren't careful and kind of slice up that dictionary of weights and try and force them into an architecture, it might work, it might not. And one of the worst case scenarios I found while testing this is it actually worked, but then I was getting different predictions out on the, when I fed samples through. So we just had to be very intentional about the way we did that. And then this problem of how to train new task heads. And really what our team was looking for was, is there something better that we can do than a very traditional data science pipeline where we have a single data set and are training up a single model to predict the categories in that data set? Because realistically, we'll never have that data set, and it's hard and expensive to maintain and constantly add on to those large data sets. And then a sort of sub-objective side quest that we had was to keep our model count down. Because our team does all of our own deployment and maintaining of our models, it adds a significant burden to our team if we're suddenly going to deploy 30 attribute models and monitor them in production. So I've been calling this weight maintenance process my Franken model process, and the team hasn't accepted it or rejected it yet, so we'll see what happens in the future. But for now, I'm going to take you through sort of 2 rounds of attribute modeling. So in this first sort of spinning up a new attribute model and training it on, say, 3 tasks, what we're going to do is some nice bookkeeping. And we're just basically going to say these tasks 1, 2, and 3, we're going to mark them as new classifier layers. And then we're going to go ahead and train it. You can tell it's trained because now it's colorful. And essentially what we're going to do with this process is now that they're trained, we can mark these classifier layers as pre-trained or fine-tuned. And what we're going to do is prepare to save them, and we'll save the core model sort of as separate weight files. So out of this architecture and training process, we end up with these 2 files corresponding to different sections of the network. Then what happens in a subsequent round where we're going to add on, kind of graft on this new task 4 onto the previous architecture. So in this example, the core model, task 1, 2, and 3 are all actually the same structure, but you can't directly load in the weights because it is a different shape than the previous one. So what we're going to do is basically mark task 1, task 2, task 3 as pre-trained classifiers. Task 4 is going to be a new classifier because we haven't done anything with it yet. And then, using these 2 weight files that we had previously, we're basically just going to start slotting them into their appropriate sections in this new architecture because of our bookkeeping. So now what happens is we have this architecture where the core model, task 1, 2, and 3 are all pre-trained, and you maintain the weights from your previous run. So now all you have is this task 4 new classifier layer that really needs to be trained up. So you go through, do the training, mark them all as pre-trained, and then you can once again save them. And at this point, you can basically use these weights and load them into an API, deploy them, and hit them in like production, and it's absolutely fine. Then when you need to add on the new task, you basically just repeat this process. So the next step is, now that we can add on these classifier layers and kind of adjust these architectures and expand to new attributes, we had to figure out a good way to train it. And what our team ended up doing is we kind of made this a fairly novel multi-task, multi-dataset training pipeline. So I mentioned before that we were trying to figure out a way to avoid those very traditional data science pipelines where you have this single data set. Because in our point of view, you can have this kind of like one data set to rule them all that has all of your categories marked in it. But for us, because we have to keep adding on things, we run the risk of adding a new attribute. And then this data set we've been sort of coddling and nurturing, it may not actually represent that new category well, which means that we then have to basically build a new data set, mark both sides with all their respective categories, join them together, which is a very time-consuming and arduous process if you're having people to basically hand label hundreds of thousands of rows all of the time. So for us, we thought, OK, what if we can take a step back and try and envision a world where we can train multiple data sets, where each data set is essentially tailored to an individual category. And this means that we could, if we can do this, it means that we can train up a new attribute simply by getting a data set for that respective category, and then very quickly we can go through and train it up and get it into our pipeline. So when we were doing this, this took a significant amount of like R&D time from our team, but once we got it going, it's actually a fairly streamlined process. So I hope you think it's interesting as well. So for this example, we'll train up a 3-class problem. So say we have color, pattern, and style. And what we're going to do is sort of prepare these data sets in whatever way makes sense for those data sets or whatever your framework sort of entails. And when you get to the point where you're generating the batches, what you end up doing is you actually take the batches from all of these data sets and kind of throw them into a grab bag and randomly shuffle them. Then what happens is, in training, you take this grab bag and you draw out of this bag without replacement. And you feed each batch one by one through whatever architecture you're trying to train. So in this case, we draw out a color batch. We feed it through our model. We're actually going to get the output probabilities from color, pattern, and style. But since this is a color batch and it's only actually marked with color, you only calculate the loss for color and use that color loss for backpropagation. Then on a subsequent iteration in this epic, you basically say you draw out a pattern batch. Once again, you're going to feed it through the model. It's going to output probabilities for color, pattern, and style. But because it's only marked for pattern, you're just going to calculate the pattern loss. And kind of the idea here is that we can let the network predict whatever it wants for color and style, but because we don't have labels for it, we're not going to penalize the network for decisions it makes on those categories. And this kind of training cycle ends when we get to, I guess, you draw that final batch out of that grab bag, and the concept is the training epic. And after you train up a model in this way, it's kind of interesting because the model at no point has seen a sample which has been marked for color, pattern, and style kind of all together. But what you get is a sort of model that performs as if that had been the case. And it means that we can really add on new categories extremely quickly. And all we really need to figure out is the most clever way to build that data set. So kind of just wrapping up and really using these methods, so the architectures and the sort of tips and tricks that we built out to kind of expand the attributes, we've been able to add on additional attribute categories. We've trained with multiple data sets and made sure to test like situations where we had unified data sets for multiple attributes and kind of trained them up both pipelines to see how they compared. And we found that our like multi-data set approach to basically get the same results, so that was good. Also trained them up on a number of domains to make sure this wasn't something that just weirdly only worked in fashion. So that was also good to hear. And we found that these sort of architectures that we built out continue to perform well across new categories as we're adding them. And the ongoing work that we have is really around trying to incorporate these attribute models into more services that we're building. So the team has been focusing on things like visual similarity, and we found that incorporating these attribute models as feature extractors on the back end for these similarity services actually improves their performance significantly. And then additional areas where we're trying to incorporate them going forward are things like in the wild product search. So the idea that users can submit photos and we return similar items in our product catalog. Then we have style personalization and outfitting as kind of additional horizon type R&D things. And of course, because it's a problem that never ends, basically we're just going to keep expanding the number of attribute categories for these models at Shoprunner. So that's my talk. And questions. And for, I guess, some context, this is our team data science logo at Shoprunner. Initially, I had submitted just the horse that Andrew Ning drew in his deep learning lecture as our potential mascot, but our director shot it down. So I basically put a pug on top of it, and he loves pugs, so that got approved. And yeah, contact info. So questions?
How many attributes do we have so far?
So currently we have 5 functional attributes. We started with 2 earlier in the year and have been incrementally adding on 3. Oh, I guess I forgot to repeat the question. The question was how many attributes we have. So right now we're only up to about 4 or 5. 5th one's being built out now. So it's been slow to sort of get traction and how to build out all the processes that go into data set building and then getting these pipelines working. So hopefully we can get up speed and start adding on attributes at a quicker rate. So that's kind of where we're at now. Yes?
With your reverse image search, are you labeling the image that they're uploading and using that to compare labels? Or are you doing an actual reverse image search, like layering?
So essentially, we're not really labeling anything in our image searches right now. So essentially, we're just taking the feature vectors out of them and using basically comparing the similarity of the feature vectors. So that's kind of where we're at now. We're not actually doing any labeling and storing of stuff. So. Oh, sorry, can't hear you.
So when you add new classes, do you freeze the weights or
So right now the ideal situation would be so the question was when we add on new attributes, we freeze the weights in the previous sections. And the ideal for us would be yes, but we've had some issues getting the new tasks to train up to a sufficiently high level while holding everything frozen in the network. So we've been kind of forced to train things at very low, very, very low learning rates in the main sections of the network to get it to gel appropriately. But yes, the ideal situation would be if we can just hold everything frozen, because then we don't have to worry about how now the models we're deploying are slightly different from the previous versions that we had in our production. So yeah, that's something that we're also kind of struggling with and dealing with right now. In the back? Oh. Let's see. So the question was something that surprised me in this pipeline. Trying to think. I think it's really been how hard it has been for data set building, because a lot of the fashion topics, even for simple things like color and pattern, it's super subjective and very kind of arbitrary. So you have to be very careful in how you're building these data sets, because decisions made very early on in that pipeline basically just snowball such that you can actually just destroy the categories that you have in your final model. So when we got started, we actually had to do several iterations of color and pattern, which were kind of the initial ones we scoped out, because we basically tried to get hand-labeled images from using figure 8, and basically we got very low quality and a lot of cross-contamination from those data sets. So when we did just initial kind of R&D, we just got terrible color categories and terrible pattern categories and didn't know what to do with it. So we kind of had to burn it down and start from scratch. So yeah.
Were there any tools or frameworks that you found yourself needing to adopt to support the multitask, multi-dataset approach?
Yeah, so I think before I joined up, the team was using a lot of fast AI, but then when I joined and started doing a lot of the multitask stuff, we found that fast AI doesn't support a lot of our needs, so we ended up building out kind of a custom Pytorch framework to do the multi-dataset, multitask training. And that's kind of something that our team is hoping to open source. We're kind of working to see which sections are appropriate and what we can actually do, because it's kind of a nifty way to solve this type of problem, although we're actually unsure of how many people have this problem, so who knows. But we are trying to open source the useful sections of the frameworks that we built out. Let's Let's see. Any other questions? Cool. Yeah, feel free to talk to me or contact me, however. Always happy to chat.